So the next speaker is Musoke, who's going to talk about high-frequency quasi-periodic oscillations and in GRMHD simulations of tilted accretion disks. Please start and go ahead.
Can you hear me and can you see my screen?
Yes, perfect. Thank you so much.
Great. Move this. Okay, so hi everyone. Thank you for the organizers for giving me the opportunity to speak today. I'm Musoke, a postdoc at the Anton Pannekoek Institute at the University of Amsterdam. And today I'm going to talk about quasi-periodic oscillations in GRMHD simulations of thin tilted accretion disks. And this work is done in collaboration with Oliver Porth and Matthew Lisker. So quasi-periodic oscillations, or QPOs, appear to be a common characteristic of accreting systems. And QPOs take the form of narrow peaks in the X-ray power density spectra, such as those shown in the power spectral density plot on this slide. And QPOs in black hole binaries can be categorized into two groups based on their frequency. Low frequency QPOs if they have frequencies in the range of 0.1 to 30 Hertz, and high frequency QPOs if they have a frequency above 30 Hertz. And in this work, we focus on high frequency QPOs in black hole X-ray binaries as they are of particular interest since their frequencies appear to depend on the intrinsic properties of the central black hole, such as the black hole mass and spin. So there's currently no general consensus on the origin of QPOs in black hole X-ray binaries, though numerous models have been proposed to explain their origin, such as those listed here. And these models offer a way to infer important properties about black hole X-ray binaries directly from observations of high frequency QPOs. And it is often remarked that tilted disks can give rise to QPOs. So in this work, we investigate whether high frequency QPOs can be triggered in tilted accretion disks by analyzing a simulation of a thin, highly tilted disk. So the simulation analyzed in this work is shown on the log density slice on the right and was introduced during Matthew Lisker's talk. The simulation was run by Matthew Lisker using the GPU-accelerated GRMHD code HAMMER, and it models the evolution of a very thin accretion disk with aspect ratio H/R is equal to 0.02 around a very fast-spinning black hole with spin parameter of 0.94. So the accretion disk in this run is initially tilted by 65 degrees with respect to the horizontal equatorial plane of the black hole. And the disk is also initially threaded with a purely toroidal magnetic field until this run doesn't produce a jet. So this allows us to essentially isolate the effect of the disk dynamics from the disk-jet interaction. And in future work, we will involve analyzing a simulation with a jet. So the simulation was also conducted at very high resolution, as previously mentioned in Matthew's talk, making it one of the largest GRMHD simulations performed to date. So as this was already briefly discussed, I very, very briefly will go over this. So here's the evolution of the simulation. So on the right, we have a log density slice with high density regions shown in red and low density regions shown in blue. And on the left, we have a 3D contour plot of the magnetization. So frame dragging induced by the spinning black hole causes the disk to periodically tear into two subdisks, as seen here. And these subdisks independently precess. And so the disk tearing is caused when the torque from the spinning black hole overcomes the viscous torque that holds the disk together. And the subdisk closest to the black hole is seen to be precessing, as seen here. And the emission from such a precessing subdisk is expected to be quasi-periodic. So we find that the disk tears 8 times over the total evolution period of 140,000 RG/C, and each of these tearing cycles is listed in this table, alongside their start times, their end times, their duration, and the tearing radius. And from this table, you can see that all of the different tearing cycles have different durations, and the disk tears at different location at each of the different tearing cycles. So we find that the disk tearing can lead to periods of more rapid gas inflow onto the black hole following the onset of a tear, and this is shown in the mass accretion rate plot below, which shows the mass accretion rate as a function of evolution time. And periodic modulations of the mass accretion rate may be associated with observable quasi-periodic variability phenomena such as QPOs. So the question is, do we actually find evidence of QPOs due to this tearing in the simulation? And it turns out that we find something interesting if we look at the longest tearing cycle, E5, which is highlighted in the red bands on the figure below and also in the table above. So in this analysis, we use the local mass accretion rate as a proxy for the observed signal. And therefore, in order to probe the structural variability in the simulation, we look at the power spectral density of the mass accretion rate. So here we show a PSD of the mass accretion rate computed for the inner 50 Rg of the disk over the time period spanning the longest tearing cycle E5. So on the bottom axis, we have the radius in units of Rg, and on the left we have frequency in C over Rg, and on the right we have frequency in Hertz computed for a 10 solar mass black hole. And the color scale represents the log of spectral power density, where yellow corresponds to regions of high power and purple corresponds to regions of low power. The white dashed dot line also shows the inmost stable circular orbit. So structures in the disk of interest in the disk may oscillate or rotate or vary at characteristic frequencies. So we also plot the Keplerian, radial epicyclic, and lens steering precession frequencies as a function of radius in this plot as well. So if a high frequency QPO feature is present, we expect to see a somewhat localized feature or localized region of very high power, so in yellow above 30 Hertz. So this plot shows that we have an extended region of high power that runs along the radial epicyclic line to the dashed cyan line. And this shows that we have a strong radial epicyclic signal across the disk. And importantly, then we also find a somewhat localized feature here at 55 Hertz, and also around 13 Rg, which is the location of the tearing radius in this cycle, signifying the potential presence of a high frequency QPO signature. So the question now is if we compute the power spectrum of the mass accretion rate at the tearing location, so along this radii, do we actually see a high frequency QPO peak? And yes, we do. So the figure here shows the average of the power spectrum, the power density spectrum of the mass accretion rate computed at 13, 14, and 15 Rg. So this corresponds to radii at or very close to the disk tearing radius. And in magenta, we have the power spectrum computed during the tearing cycle E5, so the longest tearing cycle. And then also in green, we show the power spectrum computed for a period of time in which no disk tearing occurs. So by looking at the magenta line, you can see a distinct peak in the power spectrum, typical of a QPO, and moreover, this peak occurs at a frequency of 55 Hertz for a 10 solar mass black hole, classing it as a high frequency QPO. And so this peak is clearly not seen in the green power spectrum, which is then again computed for the period in which we don't have any disk tearing. We also, on this black dashed line, plot the radial epicyclic frequency at the tearing radius of 13 Rg, which roughly coincides with the centroid of the QPO feature that we see here. Fitting power law profiles and Lorentzian to the spectra, as shown in the insert on the right, we also obtain a QPO quality factor of 11.3. So the high frequency QPO is produced around the location at which the disk tears, which supports the idea that high frequency QPOs can possibly be produced by disk tearing and tilted accretion flows. And this result provides the first detection that we know of a high frequency QPO in a GRMHD simulation of a thin tilted accretion disk. So we also compute the PSDs using smaller time intervals, which allows us to see weaker features that may otherwise be washed out over long integration periods. On the left, we have the original PSD computed over the long time period given above. And on the right, we have this new PSD computed over a shorter time period as shown above. So on the right, we see
3 minutes left.
Thank you. So on the right, we see evidence for a weaker harmonic high frequency QPO at 110 Hertz. And this frequency corresponds to 2 times the radial epicyclic frequency, so given by this dashed dot cyan line, which is also 2 times the frequency of the fundamental high frequency QPO structure at 55 Hertz that we had discussed before. So the high frequency QPO signatures in this PSD therefore have a frequency ratio between them of 1 to 2 and occur at the same characteristic radius. So the presence of simultaneous high frequency QPO peaks with a 1 to 2 frequency ratio is consistent with observed ratios of high frequency QPOs, such as those observed in GRS 1915 plus 105, for example. So lastly, this figure shows the top-down view of the disk during the tearing cycle E5. And the color corresponds to the log density, with high density regions shown in red and low density regions shown in blue. So you can kind of see in this image that the disk has torn into an inner subdisk, was surrounded by an outer subdisk, and these 2 subdisks are separated by this blue region of low density. So we find that the high frequency QPO signatures are related to the generation and amplification of radial epicyclic oscillations that are shown in these black squares. So these oscillations are found to occur on either side of the black hole along the line of nodes, which is essentially the vertical line running down the center of this plot. Oscillations are produced within this ring of enhanced density that's on the outside, the inside edge of the inner subdisk. And these oscillations that are produced in the simulation also significantly amplified during the periods of time in which the inner and outer subdisks undergo periods of significant large-scale misalignment. We also find that the QPO frequency is determined by the evolution of the tearing radius. And in this simulation, the tearing radius remains roughly constant at about 13 Rg during the time period that the high-frequency QPO signatures are actually observed. And therefore, the frequencies of the high-frequency QPO signatures that we see are also roughly constant. So just to conclude, in this work, we have found the first detection of high-frequency QPO signatures in the mass accretion rate of a GRMHD simulation of a thin tilted accretion disk. And the result implies that disk tearing may be a possible mechanism for the generation of high-frequency QPOs. Furthermore, we found the 1:2 frequency ratio that has also been observed. But this can also be can also lead to other frequency ratios such as 3:2 and 5:2 by Doppler boosting and relativistic effects. So disk tearing has the potential to be a unified model for QPO production during provided that low frequency QPOs can be produced by disk and or jet precession. So if one can then place constraints on black hole spin, if you're able to extract the tearing radius from, for example, the frequency of the high frequency QPOs, and also extract the precession period from the low frequency QPO detection. Future work will involve ray tracing the simulation data to see what the features truly look like in X-rays, and also taking into account the effects of radiation by performing general relativistic radiative magnetohydrodynamic simulations.
Thank you so much. We have time for maybe one or two questions.
One question in the room.
Okay, so let's start. One question from the room, please.
Yeah.
Hi, it's Alexandra Viledina. So my question is whether you have a special condition to form these high frequency QPOs, because we don't always see the high frequency QPOs when we see the low frequency QPOs. Are there special, mass accretion rate limits or something like that?
So I can only talk about it from the case of the simulation, for example, rather than from observation. So as I kind of outlined on this slide, that we see these sort of radial epicyclic oscillations at the outer edge of the inner subdisk. We only see these during this exceptionally long tearing cycle E5. And this tearing cycle is one in which you have really extended periods of large-scale misalignment between the inner and the outer accretion disk, the subdisks. And we don't see this in any of the other tearing cycles. And this period is not as elongated in terms of the misalignment as well in these other tearing cycles. So definitely you need sort of enhanced periods of large-scale misalignment between these things, between the inner and outer subdisks, to kind of drive the thing that is triggering these QPOs, as we see from the simulations at least.
Cool. So there's one question on Slack that I think has been answered with this question, but please take a look. And Chris, another short question, please.
Yes, a very short question. So thanks for a very nice talk and nice analysis of this part of the data. So at that tearing radius, can you just give me a brief idea of what the magnetic field structure is? Is it dominantly poloidal, dominantly toroidal? Is it a strong field or a weak field?
So in the simulation, since we threaded it with an initial toroidal magnetic field, at no point in this simulation do we actually develop a strong large-scale poloidal field. So that's why we don't get a jet here. Yeah, exactly. So
it's strongly toroidal then. Yeah. Thank you. Thanks.